All right, so welcome back to Graph Representation Learning. So today we're going to talk about how can we represent those nodes in terms of a low-dimensional vector, and that will allow us to do a bunch of things with those representations, such as link prediction, node classification, and sometimes even the whole graph classification if we found a way to aggregate those nodes into a single vector. So if we just backtrack a little bit into the previous slide and just remind ourselves about what's the problem set up here. So we just assume that we have a graph, G. This graph has a set of nodes. In this example here, we have four nodes, 1, 2, 3, and 4. Those nodes have some adjacency matrix or some adjacencies between each other, which is represented in this matrix A on the right-hand side. So the adjacency matrix is a binary matrix with 1 and 0. 1 just means that there is an existing edge in between the nodes with those particular indices here. So it's very important to remind ourselves that the constraint here is that we have no node feature so far. We don't know what's the labels of those nodes, and only the graph structure or the graph topology is what we have. So the goal is to learn some kind of embeddings, also known as low-dimensional vector representations of those nodes, so that we are able to find similarities in their embedding space, and hopefully that kind of approximates the similarity in the real space, which is the graph space in that you see here. Okay, so I think this slide just summarizes all what I've been talking about. We have a graph or an original network here, and for every single node, which are known here as U, and as an example, U and V, which is just a randomly sampled node from the network, we would like to find an encoding using some encoding function f, right, that takes us f of u, which is equal to the encoding of u, which is essentially zu, right? So zu is nothing but the encoding of u in a low dimensional space, which is a d dimension, right? So d is typically within a few hundreds of dimensions. I believe in the original paper they're talking about something between 100 to 300 is typical in this case to encode the nodes into to encode the nodes into the new embedding space here. So what we want essentially is that if U and V's are similar by some kind of mean, we can define the concept of similarity in terms of neighborhood. Maybe they belong to the same community and that's why they are similar. Then their ZUs and ZVs are similar as well. In other terms, if I compare ZU and ZV by taking either the Euclidean distance, the dot product, or any kind of metric for finding similarity between those shallow vectors, it should reflect their similarity in the original space because they share a neighborhood, then they most probably are within the same embedding space if you also project them in 2D or 3D. Okay, so the idea here again is if I know and the encoding of U and I know the encoding of V, and as a matter of fact, all the other encodings in the graph, then I'm able to do any task that I want. In case I want to find or try to predict whether there exists there will be an edge existence in the future between the random nodes in my network that I can simply take their ZUs and ZVs, feed them into an off-the-shelf classifier, and that will throw at me some probabilities between zeros and one. And using some thresholding, I can say that, well, if it's greater than 50%, then probably these two people in this social network will be friends in the near future. Okay, so it's very important to note that the encoding or my f function, which I defined in the previous slide, is not defined, and we need to define it, right? So far, I'm just talking about the problem statement. I have an original network, UV nodes from from a node set V, and I would like to define some function f, which finds the encoding of U and V, which are ZUs and ZVs in the embedding space. right? And for me to be able to do so, I need to define some notion of similarity, right? So if I am able to find the similarity between U and V in the original space, which is my network space, then I can easily translate that into a similarity in the embedding space, which I know very straightforward, which is nothing but the dot product, right? So a dot product, a high dot product between two nodes, it simply is defining what's the cosine of the angle between the two nodes, right? So if two nodes are, if two vectors, I should say, are pointing towards the same direction, then the angle in between them is equal to 0, and therefore their cosine is equal to 1, right? So let's say two vectors are completely orthogonal to each other, right? In this case, let's say that ZU and ZV over here are having an orthogonal angle in between, are orthogonal to each other, or they have a 90-degree angle in between them, then their cosine or their dot product should be equal to 0 in this case, because they are not very much similar. They are pointing to two different, completely different directions over here. So this is not what we want in this case. So I already know how can I define similarity in the embedding space. Now the next question is, all right, so how can I find the similarity in my original network, right? Which is the net, which is the embedding, which is the topology on the left hand side. Okay, so in order to do so, in order to find the node embeddings in general, or the ZUs and ZVs, I should mention that I need three things. Number one, I need to define what is my F function. In other terms, what's my encoder? What's the function that will take me from U, V, and encode it into ZU and ZV? The second thing that I need to know is what is the similarity function in my original space, which I don't know. Or all I know so far is the similarity of my ZUs and ZVs in the embedding space, which is nothing but a dot product typically used for that purpose. And finally, I should also be able to find how can I optimize the parameters of that f function in such a way that it translates this similarity of u and v into a dot product of ZUs and ZVs, right? So in other terms, I need to find a great optimizer that will find the new encoding ZVs and ZUs, which translate to the original similarities of U's and V's in the original space, right? So that's an optimization problem that we need to solve. Okay, so the first concept that we talked about is the encoder, right? Which is my function f, as I mentioned. So this will simply map each node v into a zv, or d-dimensional embedding, typically into 100 or 300 dimension embedding. And the second one is my similarity function, right? So similarity function, which I just mentioned here as similarity, which is my, which I still did not define. It will simply translate this particular metric or value into the dot product between ZVs and ZUs in the embedding space. So ideally, we would like to have an encoding of V as nothing but some column from a given matrix Z, right? And Z is nothing but a very large matrix of D by V, where every single column is the representation of the node, and every single row is nothing but the dimension of that in the new embedding space. So typically, let's say I have, as an example here, right? I have a network of 3 nodes, 1, 2, and 3. There is maybe one node which is kind of like unconnected. 1 and 3 are connected with each other, and let's say that node 2 is not really connected here with any other node in the graph. So my Z here is nothing but an n, so we should have 3 columns, right? One for each node that I have here, 1, 2, and 3. And D is the dimension that I use for in my d-dimensional space, embedding space. So let's say that D for D is equal to 2, right? Which is my embedding space over here. I have only these two nodes. So typically, I would like node 1 and node 3 to have hopefully the same network embeddings, right? So let's say that the embedding of 1 is 1, 2. Embedding of 2, because it's completely an unconnected node, let's say it is 5, 7, and 3 is a little bit different than 1, but here it should be kind of closer to 1 because they share a link in this case. So let's just say that it is 2.1 and 2.2 in this case, right? So hopefully my z dimension or z matrix here will give me the encoding in form of a column for that corresponds to every single node in my original network over here. And so the encode, if I want to encoding of every any node here, so let's say that I want the encoding of n1, right? So which is node 1 over here. This is nothing but z, right? Which is the matrix that I talked about, times v. So v is just an indicator vector, which tells me that, hey, hey, the position of n1 is in the first column over here. So it is nothing but 1, 0, 0 as the position vector or indicator vector for node 1 in this case. So meaning that, hey, n1 is the first column here. Now, if I want the encoding of n2 or n3 in this case, right? So the encoding of n3 is nothing but z, which is this matrix over here, times 0, 0, 1, meaning that my position of entry is in the last column of my my matrix, my embedding matrix over here, which is in the two-dimensional space, right? So here my embedding is in 2 times 3, right? Which is the size of my vertex set here. My vertex set is composed of n1, n2, and n3, which has my 3 nodes over here. So 1, 2, as well, and 3 nodes over here. Okay. All right. So this is the idea behind, or how can we find the embeddings from the embedding metrics that we just learned, right? So we still did not talk yet about how can we learn those embeddings, but the idea is that hopefully I should be able to learn Z. Z is the most important component in my learning process. Because that's what holds the new embeddings in a low dimensional space, representing the nodes in terms of a shallow vector. So this is my Z embedding matrix. I already talked about it. Every single column represents the embedding of the node. Every single row represents the dimension. In a few hundred dimensions, hopefully we should learn the encoding of every single column or every single node in the case of the Node2Vec or DeepWalk or any other representation learning algorithm for graph learning. So the simplest encoding so far approach is just using one encoder function, right? And that hopefully finds the embedding lookup or my Z matrix here. So there are, in fact, multiple methods that finds the exact Z matrix that I talked about in the previous slides. And all of them work differently, and the only difference between them is the way they define the notion of similarity, right? So DeepWalk, the way of defining similarity between the nodes in the original space is different from the Node2Vec way of representing similarity in the original space, which is also different from the line algorithm as well. So we're going to start with the very simple one, or the very earlier method, which is the DeepWalk algorithm. It relies on the idea of random walks, which we're going to see in the next slide. And then we're going to talk about Node2Vec. So Node2Vec is particularly more, a little bit more sophisticated than DeepWalk in the sense that it is given some different ways of defining the node similarities using the BFS or the DFS method, meaning that I can balance out two different strategies for defining similarity. So two nodes might be similar if they are within the same community, and this is known as the local microscopic view of the network, or they also might be similar if they are sharing the same structural roles in the network, meaning that, well, they might not be within the vicinity of each other in the original network. They don't share direct small hops few away from each other, but maybe they have the same structural roles. Maybe they are celebrity nodes in their local networks, which makes them similar in that sense. So we can balance out these two notions with the node-to-vec algorithm. So let's start with the first way, which is the DeepWalk algorithm here. So DeepWalk algorithm here defines similarity of the nodes in the original network using the notion of random walks, right? So here in class, let's say that I am in class and I'm calling or I'm asking the question, hey, um, Jake, how would you define node similarity? And then Jake might tell me that, well, similarity in terms of nodes are the ones that are sharing sharing some network or sharing some link between each other. Now, I might ask another person here. So I might ask Sadra, and he might tell me that, well, I think the similar nodes are the ones that are structurally similar, meaning that they are celebrity nodes, or they are the nodes that are typically connecting their neighbors together, right? So they have some kind of similar structural role, which are, and not necessarily the ones that are within the same community or share some network here. But in fact, the best way so far in the deep walk algorithm was using the random walks as a strategy here for defining similarity in the original network. And we're going to see an example of random walk in the next slide. So random walks is pretty straightforward, and it goes as follows. For every single node in my network, what do? I just randomly walk starting from that node, and and I perform multiple random walks of the same size, right? Let's say I start in this case where the smiley emoji is, which is node number 4, right? I would like so let's say my parameter of my random walk parameter tells me that, well, I would like to perform 5 random walks of size 3, right? So I can start from node 4 here, and I can go to node 3 randomly, right? I could even have chosen 1, 3, or 5 because those are the neighbors of node 4 in this case. But my first number walk chose node 3. Then from node 3, I perform the same thing. I can either go to 1, go back to node 4, or go to node 2. So let's say that I went to node 2 at random, right? So meaning that their probability is equal, right? So 1/3, 1/3, and 1/3. They have equal chance of choosing either edge 1, edge 2, or edge 3. Okay, so let's keep going over here. So and my next random walk is from node 2 to node 8 in this case. All right. So now I just perform my first random walk in this case. So let's just say random walk 1 starting from node 4 is equal to 3, 2, and 8, right? So I just said that my random walk parameter so far is perform 3 random walks of size 3, right? Or 5 random walks of size 3, right? So all right, so this is the first random walk in you starting from node 4. So I will just do the same thing again at completely random, but this time instead of starting from 3, maybe I went to 1, and I went back to node 4 because that's an option as well. And I within the same random walk, I might visit the same node multiple times. So from number 4 again, I went to number 3, right? So let's just say that I perform. This is my second random walk starting from node 2, and this is my third number walk. My third random walk this time, well, I went to node 5. From 5, I went to 6, and from 6, I went to 7. All right. So this is my random walk, random walks, and I keep doing this thing 5 times again. So R4 and random walk 5 over here. So what this constitute here, this is known as a multi-set, right? So it's multiple sets of random walk. For every single walk that I have here, what this tells me is what's the probability of the nodes appearing together in the same random walk, right? And the whole idea behind the random walk algorithm is that if the nodes have the ability or are or live in the same random walks with high probability, then we say that they are similar, right? And we do that for every single node in the network, starting from every single node in the network here. So let's say 8 and 2 appear 80% of the time together in my random walks, right? So I can easily say that, well, they are similar in this case, right? It's because they are 80%, the probability of appearing together in the same random walk is equal to 80%, which is a pretty high percentage of the time that they appear together here. So that's in other words, this is the definition of my similarity function that I talked about in the previous slides when defining the node embedding algorithm here. So random walk is or the probability of appearing in the same random walk in this case is the similarity defines the similarity between two nodes in my network. All right. So probability that U and V co-occurring on the random walk over the network should be translated in terms of the dot product of in the embedding of U and V in the embedding space, which is a low-dimensional space of D dimensions, right? Random walk embedding starts from the idea that I should be able to estimate the probability of visiting node V on a random walk, knowing that I started from a node U. So this is just a posterior probability here, which tells me by what probability I should visit node V, knowing that I started from node U here, right? So starting from node U, she should give me some neighboring, so a set of neighboring node based on multiple random walks that I performed, just like I mentioned in the previous slides. So this is my original space. So using the random walks, I should be able to provide or to deduce what's the probabilities, posterior probabilities for every single node and all the other nodes that appeared in the random walk the random walk strategies that I use, which is just a random strategy R in this case. All right, so this is problem solved. The first question has been answered. How can I define similarity in my original space? The answer is, well, using the probabilities of co-occurring of nodes in their random walks, right? So the second thing here in the random walk embedding is I should be able to translate this probability in terms of the dot product between this ZU and ZV in the embedding space, meaning that if the probability is high, then I highly want the cosine between Zi and Zj to be high as well. In other terms, I want the two vectors, the low dimensional vectors in D dimension, to point at the same direction. And ideally to have, if the probability is high, I want the theta or the theta or the angle here to be small, because a small angle simply means that their cosine is high. So a high cosine means a high probability, hopefully, and that's how we would like to translate it. So this is an estimation symbol that I'm using over here. Now that I know the posterior probabilities, I would like to translate them or to use some optimization algorithm that will find a direct mapping between the posterior probabilities and ZIs and ZJs. So I will keep updating ZI and ZJ, updating them in such a way that their dot product is high enough and hopefully approximating 80%, which let's say the value that I found when I performed my random walk algorithm in the first step. Okay, so now this is kind of a very efficient algorithm, and the first the question here in this slide that I'm answering is why do we do a random walk? So there are multiple advantages of performing random walks and using them as a similarity function here. Number one is expressivity. So in fact, uh, because of the randomness nature of walking from one node to another one, I am not really encoding or trying to have any kind of heuristic in my walk, right? So I am just randomly with equal probability of moving from one node to the next neighboring node, and therefore it has both inherently it incorporates the local as well as the high order neighborhood information. In other terms, I am equally able to either stay within my local community, right, and just visit my neighbor that shares directly a link, or I can also wander around in the network and keep going into some very far communities because that's my that's where the random walk took me in the first steps, right? So as I said earlier, when I visited node 4, I randomly picked node 3, which took me to node 2, another one to node 1. So this is my local neighborhood. And equally, I have an equal chance as well to wander around in the network. Maybe I chose node 5 and I went ahead to the second community, which you saw here, which is node 8 and node 9. So I wandered around far away from my local neighborhood. And therefore, it kind of balances out naturally with equal probability the chances of staying local or the chances of going also far away from the network. And therefore we say that these are the high order neighborhood or structural information can also be encoded thanks to the random walk algorithm. So that's the first way. It has a very good balance between local and high order neighborhood. The second advantage is that it's quite efficient, right? So we're not doing anything special. We're just randomly walking from one node to another one. It's a pretty cheap process, right? So we just need to consider another way from where efficiency stems is from the fact that we do not need to consider the nodes that never appears to get together in the random walks, right? So I do not need to store that information. So if in all my, let's say my 100 walks that I performed starting from node 4, I never encountered node 12, then I do not even need to store the pairwise information or the pairwise similarity between node 4 and node 12 because it's irrelevant. 12 is never going to be in my neighborhood on NR. So therefore, it is so the fact that I am storing only the pairwise similarities between the nodes where that appears together in the random walks, it makes this whole process and this whole algorithm quite efficient. So I'm saving a lot of space in terms of memory by not even bothering to store information about random walks which do not appear together. Okay, so the next question here is just for a feature learning process. So the idea, as I mentioned in the previous slide, our is instead of having some feature engineering process, the whole random walk algorithm, the deep walk algorithm, the node to vec is an unsupervised learning process. Why is that? Is because I have no idea about what those nodes mean, what are their labels, and what are their features, right? So if those nodes, let's say, are encoding the students in my class, and the edges are encoding whether they have a friendship in one of the social media platforms, right? I do not have any knowledge of that. All I know is they are connected using some edge. And the node is just encoding some kind of concepts which I have no idea about. So that therefore we say it is an unsupervised learning process. We do not need to have any domain knowledge about the graph, whether it's a molecular graph, whether it is a functional network graph, or a social media graph. So it's an unsupervised learning process. You just throw in the graph to your Node2Vec or your DeepWalk algorithm. It will just throw back at you what are the node encodings in the low dimensional space, without having any knowledge about the domain, or what that even graph means in this case. So in that matter, Z is what we want to learn, and which is the most important concept here. Okay, so random walk optimization is the third thing that I need to learn, right? So if I just go back a few slides over here and just refresh our memory of what we need. So we need a function that encodes the U into a V. We need a node similarity function, which we already defined so far. So similarity of U and V is nothing but the random walks, and the posterior probabilities are giving us the similarities between U and V's here. The next thing is the optimization, right? So which we still did not talk about so far. So optimizing the ZUs and ZVs in such a way that this similarity is equal to the dot product of these vectors here is is the slide that we're going to talk about next. Okay, the optimization is the last step over here. We already talked about number one and number two. The step one is running multiple short fixed length random walks using some random strategy R. So far, random strategy simply means that if you are at a node U, I have an equi chance, or the uniform distribution of probabilities between to move in any direction towards one of the neighbors, right? So with equi chance here. The second step here is we would like to collect what is the multiset of the nodes that I have visited on those random walks starting from the node U, right? So maybe I performed the random walk algorithm 100 times. The length of the random walks was about, let's say, 10. So NRU will tell me only the multiset of the nodes that I have visited, and I don't care about all the other nodes that I never encountered during my random walk. So that's why the efficiency comes from in the random walk similarity or strategy for finding similarity between nodes. So now the next step, or the last step of the encoding here, is to define a loss that we would like to minimize in order to find those encodings, ZUs and ZVs, right? And the loss function that you could see here is defined as follows. So I will iterate through all the U's, or all the nodes that I have in my vector set V. So for every single U, I'll pick only the V's that I encountered during the random walk, which is N sub R of U in this case. So as I mentioned, I do not need to encode information between U's and V's that do never appears together in the random walk. So for every single node that I have in my vector set, and for every single neighboring node, or for every single node that have been encountered from that initial node U, I would like to minimize the following log here. So the log here is nothing but the probability of V given that a ZU has been visited here, because U is my initial node that I started from in my random walk here. So in other terms, I would like to maximize this log here. I would like to maximize the probability of V given that the knowledge that Z you have is my starting node over here, and minus log is essentially minimizing my loss as a total here, because I just negated this log over here in order for my loss to be minimized as my optimization function here. Okay, so what's the intuition behind this loss? The intuition is that we like to find the embeddings, ZUs, from this loss that can maximize the likelihood of P, of co-occurrence of V and U. So I negated this likelihood here so that I can minimize my loss, or my total loss over here. So far I just defined my loss in terms of posterior probability here. Now, how can I define that in such a way that my optimization algorithm can perform some changes on the ZUs and ZVs efficiently? So in order to do so, I just need to define or parameterize this probability, a posterior probability here, by defining it as follows. So in other terms, I'm just using a softmax in order to define this probability that I have in here. A softmax will essentially, it's just a ratio, right, of the exponential of the dot product of ZUs and ZV over the total of the exponential of ZUs and ZNs across all the nodes that I have in my networks. In other terms, the probability should be high in case the nominator here, or the dot products of ZUs and ZVs, is high with respect to all the dot products of all the nodes in the network with myself, right? So in case we are similar, then my dot product is significantly high with respect to all my dot product with the other nodes that exist in my network. So if you would like, this is a ratio, or a normalization factor, is my own dot product ZU, which is the starting node of my random walk, with ZN, all the other nodes the embedding of all the other nodes that I have in my network. All right, so let's just plug this parameterized variable here inside of my loss here, which I just defined using ZUs and ZVs. And this will give us this following loss in this case. So instead, as you might see here, the yellow highlighted quadrant is no longer in terms of posterior probability, but it is in terms of the softmax function over here, which makes things incredibly easy for me because I can easily plug this into my optimization algorithm, and my optimizer will just find me what are the best Z's encoding of all the nodes U's and V's in such a way that it respects their probabilities, a high probability in case they are within the same neighborhood here. All right, so let's just read this loss function one more time and make sure that we understand this well. So the first term here, which is the blue highlighted term, is the sum over all the nodes, right? Why is that? Is because obviously we would like to find the encoding for every single node that I have in my graph. That makes sense. I should not leave out any node in the graph without any embeddings, because because I would like to have hopefully a feature space, a d-dimensional feature space of n by d, where n is the number of nodes that exist in my vector set, which is v in this case. All right, the second term here is the sum over all the nodes seen on a random walk starting from node U, right? Now I have a fixed U, and I will consider only the nodes that I met during my random walks that I performed during the second step of my DeepWalk algorithm, right? So and only in this NR multiset, which is the random walk neighbors, using a strategy R, which is just a random strategy here, I would like to find this particular predicted probabilities of U's and V co-occurring on the same random walk. In other terms, I will always try to maximize the log that I have inside of this function here, which is the softmax. I want to maximize the probabilities because I am only iterating across the nodes that co-occur together in the random walk. I am excluding all the other. I am not including here. V is not belonging to the vector set V. No, it is belonging to the multi-set of the nodes that I encountered during my random walk, right? So therefore, I will always try to maximize this softmax that I have inside here. And the maximization process is nothing but trying to find the best embedding ZUs and ZVs that will give us the highest the highest value inside of this inside of this log over here. Okay, so the optimization of the random walk embedding here is nothing but finding those ZUs and ZVs that will minimize this whole loss here, or in other terms, maximize this log part that you have here. All right. Uh, so doing this, so far what we've been talking about is quite easy for, as you might imagine, for a small graph. A small graph of few hundred nodes. This works perfectly fine. But there is some kind of expensive thing about this whole process. So in fact, if you look closely here, right? So let me just pause for a second and let you try to guess what's the problem here. I think the arrows already points to where to look at for finding the issue or the bottleneck of the algorithm already. But I think the main problem here is that I am looping twice over all the set of nodes. In other terms, for every single node in my vector set, I am again computing the exponential term of the dot product of that node with every single node that exists in my graph. So this is kind of like a pairwise dot product of between all the ends and all the ends again. So it's a very expensive. So imagine we have a graph of say 100,000 of like a million of nodes that exist in the network. Think about the meta graph or the Reddit graph or really big platforms, the social network platforms here. So it might be quite expensive. And in terms of big O complexity, this is a quadratic complexity, right? It's a square. V square is my complexity, which is very, very, very expensive, as you might imagine for a very high scale graph here. All right, so the normalization terms of the softmax is kind of like the culprit. Of course, now the next question is, what can I do? Can I make things a little bit less expensive or cheaper or significantly cheaper by removing one of the loops? And the answer is yes. Whenever we find things that are very expensive in computer science, we try approximation. And which one should I approximate? The first sum or the denominator sum that I have in my softmax? And of course, the answer should be the second option, which is the denominator part. Why is that? Is because, well, for sure, I know for 100% that for every single node, I would like to find the encodings of that node, right? So I should not, I don't really have a choice to not loop across all the V's that exist in my V set, which is my outer loop that I have in this loss. But can I approximate the vector set in the denominator, which is the of my softmax function, right? Then probably there might be the answer is yes. I should be able to approximate this. And how can I do so? Is the next slide. And the answer is a negative sampling. So now instead of trying to normalize my dot product of ZU and ZV with respect to all the possible dot products of ZUs and all the nodes that I have in my network, what about I pick only a subset, right? And this is known as negative sampling. So negative sampling works as follows. So instead of using n, all the possible n's in my vector set, I'll just pick n from a k nodes in my network, which is shown in the sum factor in the second formula over here. So in other terms, if I pick only k factors or k random samples, which I call here as negative samples, those will be the representative samples of my whole nodes in my network, right? Because at random, if let's just say that k is equal to 5 or k is equal to 10, 10 or 15, these are enough number of samples to represent the whole the whole node sets that I have in my network. So if I were just to read this as follows, so instead of using the log of exponential of ZUs and Z dot products of ZU and ZV over the sum of all across all the dot product of ZU and ZN for all the nodes V, now instead of doing that, let's just do that between ZU and ZN, and the sum here is from 1 to K, not from 1 to V or 1 to N here, just like the denominator part of the first log function over here. So the random, so if and here I'm just saying that, well, I have a random distribution over all the node with an equi chance of being picked up across the distribution or vector set V in this case. So the negative sampling is the answer, and which makes the algorithm way more simpler and cheaper to compute those ZUs and ZVs for the case of the DeepWalk algorithm here. So the sample k negative sampling k negative nodes, and you can also try to do something which is, instead of just having a equi chance of being picked up from the vector set V, you can even give a little bit more chance to the nodes which have a high degree, right? In other terms, sample k negative nodes will have a higher chance of being picked in case their degree is high, right? So which makes sense, because if a node is have a high degree, then it's probably a good an important node in my network. And so picking the ZUs and times the ZN of an important node will efficiently find a good ratio between ZU and ZV over ZU and that important node. If a node has a high degree, then I should probably give it more chance to be picked, and hopefully to normalize the dot product of ZU and ZV, which appears to be in the same random walk, right? So that's what the proportional to the degree of the negative nodes means in this slide here. Okay, so the next question is, all right, so how can we choose the K here? Of course, the higher the K, the better. And that's the case because it approximates the K even in the highest form, approximates the original network or the original set of nodes efficiently. So typically K between 5 to 20 is enough in practice, right? So K is equal to 5 all the way to or 20 is enough to approximate the whole set of nodes in my network. All right, so this is the summary slide of all the steps that we just talked about. The first step of the random walks, or I should say the DeepWalk algorithm, is to run multiple random walks starting from each node and using just the random walk strategy with the equivalent uni probability for each other neighbor of that particular node. After making the multiset of the random nodes, which is the NRU N sub RU that you see in step number 2, we then later optimize the embeddings using some kind of optimization algorithm. Typically, that's stochastic gradient descent. And the idea is that we'd like to find the best embeddings, ZUs and ZVs, after transforming this posterior probability into a softmax function. So we would like to maximize this log term, or which is equivalent to minimizing this loss function, because we are having a negation of the log term that we have here. So we also mentioned that it's quite expensive to do so, and that's because we are doing two loops over all the vertex set, right? So U across all the V's, and then we compute the probabilities of V, knowing that ZU is there, which is the initial node that we started with. And we said that we can easily approximate that by just taking a subset of nodes on the from the nodes that we're comparing our embeddings to the denominator part of my softmax function. So if you understood all these steps, then you should be able to understand how the DeepWalk algorithm performs, and how to find the embeddings from the Z matrix of which is essentially the Z's times V, which is the indicator vector of each node in the graph. So far we talked about random walks and pertaining to the deep walk strategy. There are other ways, as I mentioned earlier from the slides, to make the random walk, and that way, in case you want to include some kind of heuristics in the random walk process, like a BFS or DFS, breadth first search, depth first search strategies, then that walk becomes more like a biased walk, right? And that type of walk is typically used in other algorithms such as node to vec. So now we covered the deep walk 2013. In the next time, we're going to talk more about the node to vec algorithm, which has two more strategies, BFS and DFS, which are parameterized by two parameters P and Q. So I'll leave you. I'll leave it here for today. And please have a look at the practice handout and bring your questions to class next time. Thank you so much.